Okay, let's now consider the architecture of a pulsed radar. Pulsed radars actually, they transmit pulsed signals, so they transmit high power during a short time with a certain period of repetition. And the architecture of the system is basically we have a transmitter section, which is in this figure is actually the upper part of the slide corresponds to the transmitter, the lower part corresponds to the receiver. And okay, they are similar in conception because to transmit a pulse, what we do is, okay, we first generate the pulse in the baseband. The pulse can have phase or frequency changes, that's why we use a vectorial representation of the pulse with a real and imaginary part. And then we actually transform this pulse into a radio frequency pulse at a low frequency, IF frequency, and then we carry out an up conversion process in order to reach the final carrier, transmission carrier of the radar. Then the only thing that we have to do is to amplify up to the desired transmitted power level, and then we route this signal to the antenna. The antenna transmits the pulse, and eventually this reaches a target that produces an echo, and the scattering of this echo is actually captured by the antenna again. So now the signal is now routed towards the receiving section, which is here in the lower part. And what we have here is a conventional super heterodyne receiver where we have a low noise amplifier, a down conversion up to IF when we can actually provide most of the IF amplification of the signal, and finally conversion up to the baseband, again in IQ components, facial representation of the baseband signals. We use an important concept here, which is the match filter. It's an optimal filter for the radar reception of signals, and then we can carry out further processing, which is, for example, Doppler processing and detection, and finally displaying the information, which will show, for example, the position of the targets. So this is how radars basically work. Then, two parameters that can be obtained by the radar is range and speed. So let's begin with the range determination. The range determination is pretty straightforward. We transmit a pulse, which is a short pulse, and we receive an echo after some time. If we measure this echo delay, then we know the range, because the delay is actually related to this distance which has traveled, the signal has traveled, which is twice the distance between the radar antenna and the target. We have to go and then go back towards the radar, and if we divide by c, the speed of light, that's the delay. So we can invert this expression, and then we know the range of the target. Pulses are regularly transmitted, or almost regularly transmitted by radar, so we will consider here that we transmit as a fairly regular repetition interval, which is this capital T parameter here. And well, the pulse repetition frequency is the inverse, of course, of this period, this PRF parameter. And then another parameter important here is the duration of the transmitted pulse. This tau zero parameter is actually modeling the pulse duration. There are certain problematic cases in the case of pulsed radar that we have to consider. First one is, okay, if we have a target which is very close to the radar, the echo will be partially overlapped to the transmitted signal. In this case, we will consider that we are not going to see this target. So a pulsed radar has what is called a blind zone or a blind range. So distances which corresponds to a delay which is below the pulse duration tau zero are going to be considered blind. Okay? If the delay is increased, we can reach a point where the delay is exactly equal to the period of repetition of pulses. In this case, we have an eclipse between the transmission and the reception of the echo. Because the radar is multiplexed, it's not working, the transmitter and receiver are working at different times, we cannot obtain this echo. So for certain ranges, we are not going to see the targets. What happens if the target is at a higher range? In such a way, the delay actually is higher than the period of repetition, which is the case we have here at the right. Well, in this case, we have a small problem. The radar will consider the delay with respect to the precedent transmitted pulse. So we are going to actually, in general, we are going to estimate a wrong distance, a much shorter distance for this target. So if the delay is higher than the pulse repetition period, we have an ambiguity problem. So radar or pulsed radars are range ambiguous, and the maximum non-ambiguous range here can be calculated just translating the repetition period into a distance with this parameter here. So most of the radar are designed in such a way the targets of interest falls in a non-ambiguous range. Then, when we receive the echo, we can process this echo in different ways, and one of the important parameters is, okay, the receiver has a limited bandwidth, and this is defined by a filter. So one of the interesting questions here is, okay, how should we design this filter in such a way we obtain the maximum signal-to-noise ratio? Okay, let's analyze this problem. The output of the filter actually contains a signal, which is this blue, and a noise component, which is this red line here. So our intention here will be to maximize the target peak amplitude here with respect to the noise level. Okay, how to do that? Well, let's define the signal-to-noise ratio in a radar way, because we are not interested in the signal average power. We are interested in the peak power of the signal. So the signal-to-noise ratio in radar is defined in this way. So the signal term is actually instantaneous peak signal power, and that's divided by the average noise power. Noise power is not peaking anywhere, so it's supposed to be a stationary process. So in this case, that's the average power here. By the way, the average power of the noise depends on the system noise temperature, or the total radar temperature, and we can actually model this with a flat or wide spectrum. And the constant here is, and this N0 is just the product of the Boltzmann constant by the system temperature that we have in the radar. Now, the question is, what should be the optimal filter in order to have the best possible signal-to-noise ratio? Well, the answer is a filter that actually provides at its output the signal autocorrelation, and that's the expression of this filter. That's called the match filter, and it replicates with some changes the signal. So actually, in frequency, the match filter is just the spectrum of the signal conjugated. In the time domain, it is also conjugated, but we have also a change of sign in the time axis. Actually, we can build different match filters with different technologies, resulting with different gains and delays. So the gain here is modeled by a constant k prime in this case. A possible delay of the filter in terms of frequency, it's just a linear phase, which is this term. So to simplify our formulation, we will consider simple assumptions for these parameters. So we are going to take k equal to 1, and the delay we are going to assume it has a no delay filter. Okay? Although in practice filters will have some delay, have to be causal. So, but this can be both parameters. If they are not 1 and 0, they can be easily calibrated, and then they can be taken out from the analysis of the signals. So, okay, let's assume these simplifying parameters for the filter, and let's see what we obtain. Actually, with the match filter, what we obtain is the best possible signal-to-noise ratio. It is 2 times the energy of the echo divided by the noise spectral density, unilateral spectral density N0. And then the energy is actually can be computed both from the time or the frequency domain with these expressions. And okay, that's what we get. That's the optimal value we can obtain. Then, okay, we have to do a modification before we can use this expression actually to obtain signal-to-noise ratio when we know the parameters of the radar, like transmitted power, gain, range of the target, etc., which is the following. this matched filter expression has been derived for every possible signal. But in our case, we are talking about radio frequency signals. And in radio frequency signals, power is not specified as instantaneous power. Power in radio frequency, like any alternate current signal, is normally specified in terms of effective power or root mean square power. This means the power is not computed at the maximum voltage square, but it is actually averaged in one cycle of the carrier, of the radio frequency carrier. So in this case, the RMS power is just 1/2 the instantaneous power. So if we now apply this consideration in our case, signal-to-noise ratio after the match filter is actually the half of the instantaneous peak power value. It's just energy of our echo divided by N0. And that's the expression we are going to use, because every subsystem is specified in radio frequency in terms of effective power. Almost never it's specified in terms of instantaneous power. So let's use RMS power for our definition. So now we have the ratio between the energy of the echo divided by N0, spectral density of noise parameter. Now, let's use this expression, because the energy of the pulse is just the product of the received power, RMS power, multiplied by tau 0, that's the duration of the pulse. And then we have the expression of the received power we have seen before in the radar cross-section chapter. So now if we cast now the received power here in terms of the transmitted power, the gain of the antenna, radar cross-section of the target, etc., we get this important expression. So that's the signal-to-noise ratio that we obtain in our pulse radar when we observe a target at a certain distance, certain gain of the antenna, certain noise temperature of our radar. That's what we get in the best condition using the match filter. Now, let's do some simplifications or some particularization of this general expression. With ground radar, the beam of the antenna covers, in general, a very important part of the ground surface. So this means that antenna temperature for ground radar is often considered to be T0, which is the average temperature. That's not going to be true for a space application radar, for example, but for ground radars that is often considered like this. So in this case we can just substitute the total temperature by the product of the reference temperature by the noise factor of the receiver, okay, F. Now, in the case we have a radar that that obtains a signal and a noise part, we can actually split the signal and the noise part of this equation with this two group of parameters. So the signal part actually involves the transmitted power, gain of the antenna, etc., and the noise power after the receiver. It is actually the product of the noise spectral density multiplied by the bandwidth of the filter. That's the bandwidth which is defined by the match filter. We have here a rho parameter which relates the pulse duration with the bandwidth, and we are going to see this parameter in a following chapter. Now, we have said that the match filter is optimal because it obtains the autocorrelation of the pulse at its output. Actually, this is the case we have in here. So when we calculate a convolution with this expression here, which is actually a conjugate and the change of sign of the time axis, then what we get is certainly the autocorrelation of the pulse. And that's very interesting because actually it alters the shape of the pulse and obtains at a certain point a value which is representative of the energy of the pulse. So the maximum of the autocorrelation is actually the energy of the signal. So if we take, for example, a rectangular pulse, which is a simple pulse that some radars use, okay, we have the pulse has a duration tau 0 here, that's a rectangular pulse. The autocorrelation has a triangular envelope, so that's the output of the autocorrelation. We have a change of the shape, but the duration of this triangular signal is more or less the same as the original. And this happens because that's a very simple signal, where the bandwidth of the signal is the inverse of the duration. Okay? This happens with simple signals like Gaussian pulses, rectangular pulses, and so on. There is another class of signals which are very interesting to be used in radar, which is the spread spectrum signals, which has the particularity that the product of the duration multiplied by bandwidth is much larger than 1. For this class of signals, actually, what we obtain is both the time duration of the signal and the bandwidth are large. That's why the product of both parameters is much larger than 1. And actually, the time expansion or frequency expansion of these signals is provided in general by a nonlinear phase characteristics of these signals, which is plotted in here. So that's the spectrum of a typical spread spectrum signal. Well, just an example. That's a noisy example. Can be other shapes. But it's representative of what we are going to use for spread spectrum signals. So when this happens, when we fed a match filter with this kind of spectrum signals, spread spectrum signals, what we obtain here is the autocorrelation. And the autocorrelation, because we multiply by in frequency domain by the conjugate, what we obtain here is the modulus square of the spectrum of the signal. That's the autocorrelation in the spectral domain. And actually, this results in a flattening the phase. So the phase variations is lost in the autocorrelation, and that's why the signal is actually compressed in time. When we look at the autocorrelation, most of the energy of the signal appears into a very short interval, delta tau is the duration of this interval, and this is actually reflects a time compression. So we have a wide pulse here, a long pulse, and after the match filter it results in a very short pulse. And the peak of the autocorrelation contains the whole energy. So that's why the filter is optimum. Now we can define here the compression factor, this rho factor that appears in the previous expression, which is the ratio between the duration of the pulse, the original duration, and the duration of the autocorrelation, which with this kind of signals is much smaller, and this parameter can be much larger than 1. And that's interesting to be used in radar. Why? Because the energy increases with the duration of the pulse. So in radar it can be interesting to use a long pulse in order to have a very high energy. But the resolution, the space resolution, is actually depending on the width of the output of the match filter. And that's not the original duration of the pulse. That's this delta tau parameter. If this parameter can be very small, then the range resolution or time resolution of the radar can be very large, and we can actually discriminate very close by targets. So the range resolution of the radar depends critically on this autocorrelation width parameter. This is what we see here in this slide. We have two close by targets here in front of the radar. The separation is small, this delta R parameter. Now we want to separate these two targets. Okay, let's observe the echo signals at the output of the match filter. So we see here this autocorrelation shape here is duplicated because we have two targets. These two targets will be separated if the separation, the time separation, this delta TR, is higher than the duration of the autocorrelation, this delta tau parameter. So, and this delta tau is the inverse of the bandwidth of the signal that we use. So if the separation is larger than delta tau, we will discriminate the targets, otherwise we will actually not discriminate, we will consider we detect just one target. So the range resolution limit is just to translate into range in meters this time parameter. So range resolution actually is simply the speed of light divided by 2 times the bandwidth, because the time resolution is just the inverse of the bandwidth if we use a match filter. So in summary, the match filter provides not only the best possible signal-to-noise ratio, it provides the time compression when we use these spread spectrum signals, which are very interesting to build high-resolution radars. One of the examples of this signal is a chirp pulse, which is actually obtained by changing the frequency. This is a linear chirp in this example, so we change the frequency in during the pulse. The pulse has a duration tau 0. So this is the evolution of the frequency, is a linear one, and you could see that this is actually obtained with a parabolic phase or quadratic phase modulation of this pulse. So if we have a rectangular pulse and we introduce a parabolic phase, the instantaneous frequency is a time derivative of the phase, and because this is quadratic, we obtain a linear trend of the frequency, which is plotted here. Then what is the bandwidth? Well, the bandwidth is just the slope of this line, which is actually this k parameter here, which defines the depth of modulation of the linear frequency. And okay, if we multiply k by the duration tau 0, that's the excursion that we have here in the frequency domain, and this is equal to the bandwidth of the pulse when the modulation is significant, of course. Then, interestingly, the chirp autocorrelation is very narrow, as we advanced before, because the matched filter is actually cancelling this quadratic phase behavior, which appears also in the spectral domain. And then what we obtain is, okay, after this is the original chirp, that if we filter this signal with a match filter, we have this impulsional response, then we obtain the autocorrelation, and indeed it is very narrow. And the duration of the delta tau autocorrelation is the inverse of the bandwidth of the chirp. So if we want a very high resolution in range, we can increase the bandwidth, and then we obtain it. Actually, radar engineers did not invent chirp signals. Nature did. And bats emit and process acoustic chirp signals, ultrasonic signals. You could hear an example here. Okay, so these are ultrasonic acoustic chirps, and these chirps are non-linear, like the advanced radars use nowadays. So using non-linear chirps, we can model the side lobes of the autocorrelation, and actually this is an spectrogram of the sounds these animals emit, and you could see how this instantaneous frequency changes along time. So you could see that this is a decreasing frequency chirp, and it is non-linear. This is the fundamental, and these two lines here are the harmonics of the fundamental. So they use chirps, and they process the echoes. We don't know how exactly, and they process the echoes in such a way they can interpret their surrounding and chase insects at night. Other compression waveforms apart from the chirp exist. Of course, there are binary phase codes like Barker codes. There are polyphase codes like Frank and other codes. Also, signals that are used in communications like OFDM or pseudo-random sequences are also used as spread spectrum signals for high-resolution radars.